Great, and thanks for attending this session. So, I'm Gary Evans. This is Nishkay Kathari. It's actually our first time presenting at one of these developer conferences, so I'm very excited to be here and be part of the community. So today we're going to talk about our feasibility project, I guess, of integrating learned indexes into PostgreSQL. Sorry about this. It's not a completed project or a proposal in any way. It's more of a open investigation into whether the benefits that learned indexes have shown in academic environments or studies and controlled environments still hold up when, I guess, integrated into the realities of PostgreSQL's architecture, workloads, and constraints. So learned indexes like Alex, RMI, PGM, that we'll talk a little bit about, have performed very well in academic studies. But as we know, there's a lot of complexities associated with databases like PostgreSQL that these studies don't really explore. Things like MVCC, Planet integration, concurrent updates, and many, many more. So our goal with this project was really to answer some questions like, can we integrate a learned index into PostgreSQL? If we can, what's required to do that? And if we do manage to do it, do those benefits that they've shown those academic studies still hold up? So I'll hand over to Nishkay to run through the agenda. We have only got a single mic, so we'll be passing backwards and forwards, so I apologise for that a bit.
Hey, thanks, Gary, and hello, everyone. So in this session, we are very going to talk about these exciting areas and starting with the motivation, so why we are looking for the alternatives of PostgreSQL strong, well-established index mechanism. Apart from that, we are also going to talk about the basic idea of learned index, how they can help us to quickly find the data using the models. And we are also going to highlight the few key study papers which bring the entire concept in light and also help to make the entire concept more mature. And at the end, we are also going to share our own thoughts, how we can integrate the learn index inside the PostgreSQL and few key challenges which we have encountered during this process. And also, I would like to request, if you have any question, please ask the question at the end of the session, so we will be able to finish within a timeline. Thank you.
Right, so I think learned indexing is arguably the most important performance optimization in PostgreSQL. There's been a ton of enhancements over the years, huge investments right from the index access method API to abstract indexes away from the core code. And if we look at like the B-tree index in Postgres, there's layers of optimization. So we've got the layman and YAL for concurrency. There's a B-tree plus for better range query performance and storage. And then specifically around Postgres' B-tree, we've got things like heap-only tuples, B-tree index deduplication, and parallel index scans, and many more. So given that and that other ASIC compliant relational databases out there invest heavily in traditional indexes, I guess the question, Nishkay, is what's the motivation or why look at alternative approaches?
So there are so as I worked full-time DBA in the past, so I encounter this issue like when we specifically with the traditional indexes like B-tree, when we're dealing with the large data set, they always struggle for the optimal performance. Apart from that, let me walk you through the other challenges like so in this modern world where the data is increasing at an incredible rate and data is not just getting bigger in size but also getting more complex. And due to the high demand of the IoT data analytics as well as the cloud systems, our databases are now dealing with the more complex data types where the traditional indexes are not designed to handle this kind of complexity. And for example, time series data has grown so much that the new technology called the timescale DB emerged to handle this kind of data to effectively. Apart from that, in this world of competition where the performance is always, a matter more than ever, and where all the users are expecting their query faster execution, as well as many business decisions nowadays are completely rely on the database speed. So, and that is the reason we are motivated to look beyond the conventional approaches. And Next one is like we have seen the recently massive shift towards the data-driven optimization, and the tools like DBTune which is AI-based database tuning tool, going to analyze your data, and based on analysis, it is going to auto-tune your PostgreSQL instances. Operator also doing the same kind of auto scaling based on the usage pattern. So I think indexes should not be left behind from this particular trend. And learn index powered by machine learning model could be the big step towards the efficiency and performance. Next one is machine learning growth. So we have seen massive development, or I would say the massive improvements in a machine learning industry. And thanks to the modern infrastructure where all the tools are easily accessible and scalable. Machine learning also has the power to automate as well as the optimize the things very easily, which is not possible to do if we talk about in the past. And I think this is the biggest reason that we are seeing the massive impact of AI in across the all domain.
Yeah, thanks, Nishke. And when we started looking into this a little while ago, we did do a bit of a search through some of the community forums, and we did see back in 2017 and 2020 that there was a bit of investigation into whether it was feasible to look into learn indexes at that point in time. 2017, 2018 was around when one of the probably more significant papers came out from Stanford around the RMI model. And then more recently in 2021, there was some comments, and one in particular I quite liked, that, if I understood the author correctly, was saying that a lot of these academic models hide a lot of risk behind perfect assumptions. And a lot of those perfect assumptions about those synthetic data sets can result in, miraculous gains and things that don't really apply to the real world. And that turned out to be quite true. We did see some databases that had implemented some of these indexes based on academic performance, only to find out that they didn't perform very well in the real world. So we saw some where suddenly there was latency was 3 times more when run against real world data compared to the synthetic data sets used in academic studies. So there's a bit of truth to that. But so in the end, the community we didn't really see much progress in this area, but given that that's 4 years ago, there's been a lot of changes there in many different areas. Nishke, do you think we're sort of at a tipping point now where maybe it's worth looking into this?
Absolutely, and I'm completely agree with all the concerns highlighted by the community, because as they criticize the academic model, which assume the perfect knowledge of the data distribution, and I think they are absolutely right. Additionally, you also mentioned that in the real world we are dealing with the uncertainty, like the skewed data and many more cases. So I think it is very difficult to predict everything is going to be as per expectation. On top of that, it has been proved that Learn Index showing the fantastic result with the synthetic data workload, but often struggle with the real life data by increasing the latency. So, but the most interesting things, Gary, I would like to highlight here, that the things are changed rapidly, and the models like Alex are become so robust and adaptive to the changes. So, and also have the B-tree like a fallback mechanism as well. So in case, due to any reason, the prediction got failed, but it will ensure that your performance will not be collapsed. So we can additionally we can also reduce the risk highlighted by community by looking into the hybrid approach. So we can use the Learn Index only for the hot paths, or by combining with the traditional indexes. So all the concerns highlighted by community remains valid, no doubt about that. But I think we have a better tools to handle those concerns effectively. And I think, in my honest opinion, we should the Learn Index is not only for the academic study anymore right now, and we should think seriously about integration with the PostgreSQL.
And I guess if I didn't agree with you, we wouldn't be here doing this presentation. So maybe now's the time to introduce the concept of Learn Indexes, which is really, I think, to switch thinking away of thinking of the data that we're indexing as being a black box. And the idea is, if we can lift the lid on that box and understand the data better using machine learning, we might be able to find faster ways to access the data we're after than using those more traditional indexes. So I've borrowed a bit of an example or an illustration from one of those early studies that shows a B tree as being a very simple hierarchical structure that we pass a key into at the top, and it gives us a position and a sequence of data that then we can follow some pointers or a binary search or something to find the data we're after. So given that, Nishke, how would a learned index compare to this?
So I must say that both Learn Index and B-tree has the same goal. They help us to quickly find the data by using the key. But B-tree index using the hierarchical structure and search through the levels of node to help us to quickly find the data. But Learn Index using the trained machine learning models to predict the key location directly.
So maybe just to make that a little clearer, I've got an example here, also borrowed it. Here's a B-tree index. It's being used to find a key of 110, and it's reasonably quick. This is the way we normally do it. We're using this index to find our key. I'm going to lift the lid on this example and share the data distribution with you. If we have a sequence of integers from 1 to 10 million or whatever, how by knowing that information is the learned index going to help you find that data that we're after quicker than what we can do with this type of B-tree?
So as you mentioned that a Learn Index is like a black box and using the hierarchical structure to quickly help us to navigate the data. And for that, it needs to go through these levels of node. And even though we know something about our data, but with the Learn Index, we flip the idea. If in your data, you know that how the keys are distributed, you do not require to go through the whole B-tree. We can skip all these things and jump straight to the answer. So let me give you a very basic, simple data distribution example. So Learn Index using the simple linear function to predict the key location, and which tells us which page we need to go, and in that page where we need to look for the data. So So the thing is like this is the power of Learn Index, and with the help of this, we can quickly able to find the data, and it will improve the faster performance as well. And so if you know your instead of traversing the whole B tree, you just simple calculate the based on a simple linear function, and you go straight to the key. So this is the very basic example, as I mentioned that, and only for the simple data distribution. If the data distribution is more complex, then the logic and the way of working a little bit more complex as well.
And obviously a simple linear function like that might work for such a simple basic distribution. And we will talk a little bit about some of the models and how they handle more complex data distributions. But hopefully that gives you a little bit of idea about the concept behind these types of indexes. Here's a timeline of some learned indexes that Nishke and I looked into, some studies around it. It's just interesting to see from the early ones in 2017 and 2018, where they sort of focused on that basic model design and optimization, to papers more recently where they're focusing on addressing real-world issues and integrating into emerging technologies. This is only a subset of papers, but you probably noticed that the velocity of the interest in this area has accelerated over time as well. When we heard we were able to come over and attend this conference, we thought, let's do a bit of a search and see if there's any research locally and in Canada around this. And we did come across this summary of a conference for very large databases held a year or two ago in Vancouver. And it was really interesting to see that there was more than 11 papers accepted at that conference around the topic of using machine learning for indexing in databases. Obviously, there was other papers as well that covered the use of machine learning in databases, but I thought 11 papers, that's pretty significant and an interesting point. So I wanted to share that today. I think next up, maybe we talk a little bit about why PostgreSQL is such a good platform to test this out on.
So there are the various reasons which indicates that the PostgreSQL is very well positioned for adapt and support the Learn indexes. So let's start with the first PostgreSQL extensibility nature, which allows the developer to add the custom index type. It means that we can do a lot of experiment with the Learn indexes without worry about the rewriting the PostgreSQL code from the scratch. The next one is a growing AI/ML ecosystem. So PostgreSQL has extension like PostgreSML and PGAI. This kind of extensions can capable to bring the ML capability inside the PostgreSQL database. Apart from that, This kind of things will definitely it will indicate that the PostgreSQL's readiness for the machine learning complex application. Next one is the declarative partitioning and brain. So this concept helps the user to bring the large data set into the small manageable pieces and also improve the scan range efficiency. So this concept is not a new. It's there since many years, and I'm thinking it's definitely it will work with the learn index. Concurrency control, and specifically the multi-version concurrency control, will ensures that the learn indexes remain consistent and usable, even the data keeps changing. And this is very important because machine learning models are very sensitive towards the data changes, and that is the reason it is good to know that it provide assurance for that. Rich indexing framework. So. As we all know that and agree that PostgreSQL has a strong, well-established index mechanism and it also provides the wide varieties of the indexes like B-tree, Brin, Gin, JST, and few others. So this kind of rich indexing framework provides the flexible foundation to integrate the learn indexing along with the traditional index methods. Next one, and I would say one of the biggest reason for the popularity of PostgreSQL is its vibrant and active research community. So this community members are always looking for the database optimization opportunity, and this kind of initiative will definitely drive the development and improvement of learn indexes. So I think PostgreSQL has all the right ingredients like tools, flexibility, features, and community support to be a strong platform for the learn index research and development.
Yeah, and I think many of those reasons are the reason so many of us like using PostgreSQL anyway. This slide here shows the lineage of learned indexes up to 2024. I took it out of a paper titled A Survey of Learned Indexes for Multidimensional Space. As you can see, there's a lot of indexes there, and there's been a few more that have been created around this. It was quite surprising. So this created a bit of a difficulty for us when we're thinking strategically, how do we do this? Do we just pick one or two indexes to try and integrate into PostgreSQL, or do we try and develop an index agnostic, holistic framework to support future indexes, given that this area is still fairly academic and experimental? We ended up taking the first approach and say, let's just pick one or two that have got good community backing, well, good academic backing, and good benchmark tests have been thoroughly used, and just try and integrate that. So that's what we did, and we picked Alex, which is an adaptable learned index, and Kami, which is a case-aware RMI or recursive model index type. We picked these two because they were quite different. One's static and one's adaptive, so each is suitable to a different type of workload in PostgreSQL. The difference really with a static workload, a static index needs to be trained. So you train the model, adjust the weightings, and at the end, when you reduce the error enough, then you can infer it or it's usable. The issue with this type of index is that as we insert data and delete data like in PostgreSQL, the error prediction increases, and that makes it slower, and it's no good, and it needs to be retrained. So that introduces a whole lot of complexity with model lifecycle and handling that. Whereas an adaptive index doesn't need pre-training, it's trained as you insert data into it. So that one's a little easier, or we thought, to integrate into PostgreSQL to start with. So I'll just go into a little bit of detail first around the model to give you a bit of background. I won't spend too much time on it because we want to get into the integration side. So starting with our RMI, because of that retraining, we figure, well, that's good for read-heavy workloads where we're not changing the data too much. It's fairly static. And then, if we go to the next slide, the basic type of recursive model index, and it's called that because it has layers of models, and this is sort of a structure that came out in one of those early 2018 papers by Tim Krasker and with association with Stanford University. And it has multiple models in this way, where the model in the previous one selects a model in the next layer, which selects a model in the next layer until you get to equivalent of a leaf node. And that will then predict the data position in the array or the sequence of data that you're looking at. The reason they sort of went with this structure is to do with the last mile search. So you saw the example of the linear function that Nishike gave earlier, works for a simple pattern like that, but can you imagine trying to use a single linear function to go from, say, 10 million rows down to 10 or 100. That's going to be really challenging. But it's not going to be quite as challenging to use a model to go from 10 million down to maybe 100,000, and then use a different model suited to the data within that last set to get down to 10 or 100. So that's the concept behind that model. We decided to pick the case-aware one for a number of reasons. So I had a couple of optimizations to suit some of that real-world data set degradation that we mentioned earlier. And that was really due to having to try and fit cumulative distribution functions, or CDFs, to fairly fixed large amounts of data in those leaf nodes. So what they did is they reduced the size of the leaf nodes to much smaller and made them variable so you didn't have to fill them up with data. That way it's a lot easier to fit a CDF to that piece of information, therefore reducing the error and less cache misses. The second optimization they made was to make all the internal nodes and the leaf nodes 64 bytes, so they fit into CPU cache much more efficiently, again improving the performance. So I don't want to get too much into the details because we want to move on to the integration side, but I just want to sort of give you a bit of an overview on how the models work. So I'll just hand over to Nishike, who can go through the basics of the Alex model.
So, Gary, before I just start to talk about Alex, I would like to walk you through the workload, which requires a lot of writes, or I would say the mixture of the read and write, and it's very perfectly suitable for the OLTP workload. So this kind of workload is very, appropriate for the platforms like e-commerce, banking, or booking, and a few others, which requires the lot of data keeps changing and also require the quick access of it. And I think B-tree index are one of the popular index for that because it is more reliable, but it often struggle when the data keeps increasing. And that's why the learn index comes into the consideration, and the model like Alex are very adaptive to the insert and update operations. So it makes the ideal choice for the write intensive workload. So this is the architecture of Alex. Alex is a learn index model built on the RMI, and where you can see these small nodes act as a small machine learning models to predict the key location, as well as also act as a smart decision tree. At the leaf level, Alex using the gapped array along with the free space to accommodate the insert operation smoothly. So in case, due to any reason, if the prediction got failed, then Alex will perform the exponential search to quickly recover from it. But the thing is, what makes Alex so special? The answer is its adaptive nature. So if any node is too empty or too full, then it will automatically retrain or split. And that's the reason Alex can capable to handle all the DML operations effectively. So in short, Alex has all the capability for the faster key prediction along with the B-tree-like flexibility. So it makes the great choice for the dynamic data workload. So now in the next few slides, we are going to share our own thoughts how we can integrate the learn indexes inside the PostgreSQL.
Yeah, thanks. But before I get into the implementation details, I just want to talk a little bit about the architectural design compatibility. We talked a little bit about what these indexes, Alex and Kami, look like. By the way, Alex was written by Microsoft a while ago. I should mention that. But what we didn't really look at was architectural alignment or how easy it would be to integrate these in when we decided to pick these two indexes. But the next step we wanted to do was really integrate it by creating an extension as a wrapper around one of these indexes. So we chose Alex. As a wrapper and calling the API functions on Alex, the idea was to make it a little bit simpler on us. We hadn't implemented a index via the index access method API, so we were a couple of reasons we went that way was, one, to avoid having to get straight into understanding the index page layout and detail and the buffer manager and things like that, until we got familiar with that whole AM framework and familiar with running Alex and its capabilities. So that's why we went that way, and then the idea was that we'd do some more tighter integration next time around. But it came apparent pretty quickly when we're looking at how the index access methods worked and the architecture for the ALEX index. It's obviously everything's in memory in ALEX. It's all designed in memory and done there, which is very different to PostgreSQL. I mean that approach in memory is good if you're dealing with technologies that follow those design principles, so something like DuckDB. But Postgres is disk first, and then we use caching to get performance out of it afterwards. And became apparent that with this architecture, ALEX, without a lot of modifications to the way the index works itself, wasn't going to play very nicely. And that's not an issue with PostgreSQL. That's PostgreSQL, I guess, trying to be durable, battle-tested, and engineered to be reliable at scale. And we're sort of looking through how to utilize the index access method API. It obviously tries to enforce that and guide you to follow those design principles or constraints for that type of architecture in PostgreSQL. Maybe you give a couple of examples of what we mean by that.
So in this slide, we are going to talk about some of the issue we saw in our in-memory only version of ALEX in PostgreSQL. So let's start with the scalability. So as we all know that PostgreSQL can be used for the larger database, and database size can be in terabytes, and in that bigger size database index size can also be in a gigabyte. So it is not possible to keep everything in inside the memory, and that is the reason that PostgreSQL uses the shared buffer along with the LRU caching concept. So that concept will only frequently use pages inside the memory, which improves the performance without compromising the durability. But in ALEX, if we want to keep many indexes inside the memory, this is practically not viable solution. Next one is the durability. So as we all know that PostgreSQL is asset compliance database and supports the durability. So it means that any transaction is committed. So all the changes, including the index related changes, must be crash safe, and PostgreSQL uses the WAL files and checkpoints to write those changes, or I would say the updates inside is on the disk, but ALEX is on a memory, right? And if due to any reason the system got crashed, then either we have to lose all the data, or we have to rebuild the index from the scratch each and every time. That is not possible practically to do this kind of repeating work on each and every time. So next one is the architectural consistency as well. So PostgreSQL treats the index like all the other database objects, and we can also able to get the size of the index by using the system function like PG index size. And other tools like the rebuild, vacuum, analyze, all will work as it is with the all indexes, because PostgreSQL is built on the disk first design concept, where the ALEX is not following this particular model. Gary, interestingly, you mentioned talk about the DuckDB, and I would like to highlight that the DuckDB also have the ALEX as an extension, but it works very perfectly over there because it follow the in-memory model architecture. But unfortunately, as of now, PostgreSQL is not follow this particular model.
Yeah, so thanks. So that left us in a bit of a predicament. We'd implemented our extension that sort of around an in-memory model around ALEX, which we realized, well, look, this isn't going to meet any of the typical use cases that we use traditional indexes for, like indexing persistent tables. And also, we'd sort of learned enough about the index access method API that we knew without massive changes to how ALEX works, that we weren't going to be able to effectively tightly integrate it. So we looked around at some other options. There were some other studies and papers that tried to do a persisted version of ALEX. Unfortunately, most of those papers, like AULID, hadn't reached a prototype. It was all just to theory, or those that had reached some sort of implementation, when we did some benchmarking of them, didn't match the performance of PostgreSQL's B+ trees in the database. So we're a bit stuck in heading in that direction, and we'd already done this work developing this extension around an in-memory model that sort of worked, but wasn't really addressing the problem that we're trying to. And we didn't want to throw that away, so we thought, well, are there some niche use cases in PostgreSQL for a temporary in-memory index that you throw away after using it? So we did We did think of a few, and we haven't validated these yet. This is probably the next step. So I saw crunchy data a while ago in an article by Kevin or Keith, I can't remember, about PG Parquet. Looked really interesting. So you could export and import PostgreSQL data to Parquet files. That was pretty cool through copy commands. So you thought, well, maybe if for joins and things in there, it would be good to generate an Alex index because it's very, very fast compared to a B-tree index to build. So maybe there's something there we can do. Also, temporary indexing for intermediate results. So if you have some very large, long-running analytical workflows, maybe if you're running a common table expression or building a materialized view or a temp table in there, there's a case for quickly creating a temporary index in there and utilizing that to find data quicker. Same goes for ingesting large amounts of sorted data, maybe like logs or time series. When you're ingesting that, maybe you want to do a lot of processing again, create a temporary index. So. And then there was a few other ones we're thinking, well, you got foreign data wrappers around external data sets. Maybe we could generate temporary indexes around that to do temporary joins. There's also machine learning feature store pipelines. So when you're ingesting huge amounts of data and trying to build features out of that data, it could be worthwhile building some temporary indexes on that data with which you can build those features. Another one we came up with, PG vectors, very popular now. Approximate nearest neighbour operations and things are quite expensive. Maybe a temporary index like Alex we could use in memory to, based on metadata, filter that data down smaller before being able to execute those ANN type operations against. So we thought, well, let's not throw it away. Let's investigate some of these use cases, and if there's value in them, then let's continue to build this version we had. It does bring in a lot of other questions we've yet to explore about the appropriateness of the AM framework for this. I think it's pretty straightforward because it's in memory. I think it's fine to create and drop indexes quickly and that type of thing, but we do need to look at the whole sort of lifecycle management of temporary indexes in there because it's not really what the AM framework's designed to do. Anyway, so I'll hand back to you because I'm very aware of our time.
Okay, so in this slide, we just want to talk about, like, we also want to see how Alex is behaving when we are trying to move to the disk, whether it is behaving like same B-tree, what is doing inside the PostgreSQL. So for that, we have gone through some of the past research document, and we came across that it's when we moved Alex to the disk, it becomes more slower. Or I would say slower than B-tree as well. So that is really disappointing for us because we don't want to create a new index type from the scratch, but we would like to integrate the learn index like Alex to the PostgreSQL. But again, when we try to integrate the learn index Alex to the PostgreSQL more and more, and it end up looks like a more B-tree, and also losing the original functionality, or I would say the original advantages of Alex is going to be loose and only useful for the some of the special cases like read-only or the static data. There are the other indexes, learn indexes like AU, LID, HMT, HLT, and PGM. So those are indexes have with their own strength, but again, when we try to do a lot of research and reading a lot of documents came to the end that they also have the same kind of challenges. So we decided to keep our focus only on improving our simple integration and also some of the spatial use cases just Gary talked about earlier.
So thanks. So we'll talk a little bit about our implementation and what we did. The basic architecture we followed, most of these, obviously, this whole area, as I said, is quite experimental and academic, so obviously don't want to try integrating that into the core product. So the obvious thing is to build it as an extension. Most of these indexes, both Kami and Alex, are shared C++ libraries. So our approach was to create an extension with a C wrapper to access the API, to implement a new key based on the index access method framework. And that was our sort of integration into the planner and the executor and commands like create index, drop index, etc. But there were a few other areas that we realized it wasn't going to do everything we need. The cost model for these indexes is significantly different to PostgreSQL's cost model for things like the planner. So there are some hooks and things for statistics collection that the planner utilizes that we needed to consider. And so Nishka, I'll talk about that a little bit coming up. Next slide. So obviously with this, there's catalog tables that we need to update to tell PostgreSQL about our new index we're creating. So there's like the access method table, or PGAM, and then some operator tables that tell Postgres these are the operators that we support. So it uses those for sort of validation, that, verification of, yeah, those operators are supported. There's also a strategy number that we get via the OP family into the AM OP operator table, and that's based on, it looks at the predicate and decides what type of operator is it, what are the operands, and it comes up with a strategy to guide the logic within our implementation when it calls the various callback functions. There's another table that defines the procedures that are used as well within it. So that's fairly typical of any, most extensions you build anyway, because of PostgreSQL's very, very extensible nature. There's a very quick example of the strategy number. It'll look at that predicate and say, it's a greater than. The operands are integers, therefore the strategy number's 5. It'll pass that in as part of the structure to determine some of the logic internally. Next page. So this is the index AM routine. This is really it's a C structure, and this is the contract between the core code and our index implementation through the AM framework. And this is populated when we call the AM handler that we defined in the catalog table, and that will populate these pointers with callbacks to functions within our implementation, and that's how it works. Not only with indexing, but actually with heap access has a handler like that as well that gets utilized from our index. So this will define things like, for AM build that gets called when we create an index, it'll end up calling into our Alex build function with our implementation. So we'll jump on to that now. So as I said, our implementation was really a simple wrapper around the Alex index. It has a single bulk load function that you call, and into that you pass an array of template type pairs made up of T and P, T being the actual key value, and P being payload is going to be the reference to our tuple. And so what we wanted to do was scan the heap, find all the, I think in PostgreSQL it's the pointer data, stores the block number and an offset, which is our reference into our tuple on the heap. And that would fit quite nicely into our payload with the column. So we thought, well, let's utilize how B-tree does it, and that does it in a similar fashion. So it'll scan through the heap, getting the tuple IDs and populating a spool type structure. And once it's set all those up, it then builds the index tables on disk. So we wanted to do a similar thing, but instead of building those pages on disk, we just wanted to put it into array and call our bulk load function with that to build our index in memory. So when it calls it, we don't have to, the index is created before it comes into the AM framework, so it passes that in the relation type index there. So you have your physical file on disk, and I think there's that first meta page exists already, and we just need to populate it. And so our processes are, call it, we build the index in memory, and attach any optional fallbacks, which Nishka will talk about. And then that was why I sort of talked about the issues we encountered. We're thinking of serializing it to disk, but there's a lot of issues associated with it. But we think with some niche use cases, it might still be worth doing this. And then maybe we'd have to look at, well, if someone tries to update a heap value and via the insert API function, say, oh, you're invalidating the index, so we mark it as invalid. So there's still potential for that. Things like MVCC we didn't really have to worry about with the framework, which is quite good. So we just build an index on everything, and then code in the executor at the base actually goes through and decides what's visible or not for that transaction. So it wasn't, well, I mean, it was challenging for us because it was new to us, but overall the design was pretty straightforward, I guess. And then at the end it returns an index build result, which is a couple of counts. On the next slide, I want to get through these fairly quick. Yeah, so AM cost estimates really all about trying to get an appropriate cost back to the planner so it can decide whether to use the index. I'll let you talk about that.
Thank you. So generally in a PostgreSQL, like a query planner, using the AM cost estimate function to decide that whether the index is going to be used or not. So, and it needs to perform the certain checks, I would say, basic checks. How many number of rows is going to be written by the index, how costly in terms of the I/O and CPU, as well as whether it is faster than the sequential scan or not. So these are the simple checks. Is very straightforward for the index like B-tree. But when we talk about the learn index like Alex, it little bit get more complex. So in the AM cost estimate function, we'll start to collect some basic information like how many number of index has of pages and rows. After that, it will fetch the already collected statistics data like fallback ratio as well as gap density. So I will cover how we are able to derive those states in the analyze section. So once those details are on hand, then AM cost estimate function is going to calculate the sum of the important, I would say the critical cost like model prediction cost, fallback correction cost, confidence score. And once that I also need to adjust the cost, and adjustment cost is completely based on the model health. So if the model is consistent, or I would say the accurate, then we need to lower the cost to send the signal to the planner to use Alex. But if the model is drifting, or I would say the inconsistent, then in that case we need to increase the cost to signal the planner to avoid the Alex and choose something more reliable, I would say like B-tree or binary search. So once all this cost we have like startup cost, total cost, selectivity, and few others, then we need to pass all the cost to the query planner. And based on the cost, query planner will decide the whether we need to go for the Alex, or I would say whether Alex is going to be really beneficial for the query optimization or not. So in short, the overall process is ensure that if the model is healthy, then Alex is going to be used. But if model is drifting, then Alex is going to be I would say the avoided by the planner and choose something more similar and secure.
Thanks, getting a little short on time, so I'll run through some of these quickly. AM cert, which we implemented with Alex insert memory, was pretty straightforward. It passes the new tuple ID from the heap that's being passed in, so it's just a matter of passing that into the Alex API function to insert it. This is really where things became apparent to us, where we're thinking, oh, okay, we've updated the heap, and now we've got to update the index, which is in memory. If we crash right now or we shut it down, suddenly we lose that change. And we're thinking, this is crazy. Obviously you don't want to persist that whole index to disk when you're within a transaction, because it's just not going to be fast. So maybe as that example makes it a little bit more obvious about some of the issues we're encountering with the differences in architecture. Next slide, it's a little bit short. Get tuple. So the scan function, this is the index has been selected, the executor is saying, here's my key, can you give me the position? So again, it's like a wrapper type situation. There is some probing in some of these indexes, so you can do a search and get a rough idea if your prediction's accurate or not, and then go into a fallback strategy. The issue with the fallback strategies in PostgreSQL, which could be to go into a binary search or maybe fall back to a parallel traditional index on the same key, is that once you've started a transaction or a plan that the planner's decided upon, you can't just say, oh, sorry, this isn't working, let's go and use a different index. So that's something that's got to be managed in a different way, and something we're still thinking, what's the best way of doing this effectively? There's quite a few other callbacks to be implemented with our wrapper. A lot of them didn't need to be. The main ones we had to put in were the ones that manage the scan state, I guess, handled through an index scan descriptor structure, I think it is. So setting up the scan, which things like including a reference or a handle to our index and so forth, and cleaning up afterwards. So I'll hand over to you to just talk a little bit more about statistics, because I think we're getting short on time.
So as we have seen, that AM cost estimate functions using the already collected statistics by the analyze. So now let's understand a little bit more in detail. I'm not going to go into the basic concept of analyze function. I'm sure everyone is fully aware about that. But we need some special statistics to understand that how the model is well performing or not. So for that, what we can do for the Alex, like we can start getting some sampling by fetching some random keys from the index and applying the model to applying model on those keys to find out the key prediction and key location of each key. If due to any reason, if the prediction got failed, then it needs to be switched to some binary search or B tree. So based on that, it's called it's known as a fallback. And by performing this entire things multiple times, we are able to get the number of fall counts as well as fallback counts, as well as based on that, we can get the fallback ratio. We also need to do at the leaf level, we also need to do certain scans to understand how many number of empty slots are there. So based on that, we also able to get the gap density. So once we have all these things, okay, and we need to store those statistics, otherwise AM cost estimate function will not be able to fetch those things. So we have to store inside the PG_statistic table, and AM cost function will use those for the cost calculation and pass to the planner to assure that the Alex is really beneficial for the query or not. So now this slide is going to talk about the challenges which like I would say the challenges to adding the Alex cost calculation inside the PostgreSQL. So generally PostgreSQL expecting the simple optimal cost value to pick the best index by the planner. But learn indexes are completely different from the traditional indexes because it follows the learn index. It's a machine learning models as well as also rely on the fallback solution. So we need a special way to calculate the optimal value, and different kinds of workload also affects the Alex differently. For example, the workload like point lookups, range scans, insert intensive workload, all are behave in their own way, and that is the reason we need to do a lot of benchmarkings to compare the Alex to B tree in a different situation to get the right optimal numbers. So another thing is PostgreSQL expect the simple statistics, but in Alex we are figuring out as of now certain things by manually. Certain things like how many total number of slots are there, how many pages, how much pages are full. Those informations are currently we are figuring out manually. So we need to do a lot of work to help the planner to understand the Alex in a better way, and that's once it is possible, then we were able to get the right prediction from the whether Alex is really beneficial for the query, and we'll get the real benefit of that.
Yeah, definitely a key part of it, and why it's sort of titled calibration, trying to calibrate it to the right value. I'm just going to skip through to the last slide of where we're at now. If you're interested in more about the fallback strategies and what we're thinking there, catch up during the conference with Nishkay or I. So at the moment, our conclusion so far is that without modifying Alex or a similar learned index, to make it compatible with the way PostgreSQL works isn't really viable at this point in time. Everything we've done, the studies we've looked at indicate that the performance isn't going to be there. There are some very good papers that in theory look like it might be possible down the track. And, and we see we've got Microsoft and AWS investing in a lot of custom silicon for their AI infrastructure and thing. Maybe if we utilize that and some of these, maybe one day that we're going to get there. But we don't think we're there at the moment. And part of our project's not really to go and write a learned index. We're just looking at integrating something that's out there at the moment and how to do that. So we've shifted our focus a little bit. We are going to write up a paper on some of our findings. We'll release at some point. But at the moment, we're sort of thinking, well, let's investigate some of those niche cases and see if there's a value for that type of in-memory index. And if we think there is, then we're going to chase down that path. And then in parallel to that, there's still some of those other learned indexes that we want to have a look at that require training and the whole model life cycle management. Maybe just sort of thinking ahead to what sort of things do we need to do for a more generic framework if a model does happen to come out in the future that's feasible to integrate into something like PostgreSQL. So it's been a fun looking into this, a really interesting area. It's been pretty new to us. So I hope some of that's been interesting to you as well, sharing that today. So thanks for coming along to the session. I guess hopefully we've got a little bit of time for any questions out there.
Probably be available for questions afterwards, but
Yep.
we have to start vacating the room and get ready for coffee. So we won't hold you back.
All right, thank you.